Or if we got this transfer function like this, and this is a characteristic equation, and we consider the denominator here, then we got in the A matrix, we got this is 0, 1, 0, 0. All of this have 0 at the first, and you see that it look like this for the columns, the next columns. And in the last row, we got A minus A minus A naught, minus A1, minus A2, and up to this. Okay, and the B matrix like this. Okay, sorry, I still missing this, and I have to put X here and BU here. Okay, and for the output equation, we got B naught, A naught, Bn, and if the system is causal or proper, the transfer function is proper to have no B naught, Bn. Okay, I explained to you before. Normally, we will denote it. This is Sm, and we require that m smaller than n or equal. But here we denote it by n. So normally, for the causal system or proper transformation transfer function, then normally Bn will be 0. Okay. So this is the first, the canonical form. We represent it very easy. If we got something like this, so we got A1 is 3, A naught A2, so we just put minus A naught minus A1. Okay, not something like this. Similar to this, so we got here A2 E4, A1 is 11, and A naught is 9, so we put minus 9 minus 11 minus 4. Okay, so just 9, 11, 4. Okay. Of course, even when we got Bn, then we have to take care of this. But for A, it doesn't change. But for B, for output equation, you have to take care of the output because we have Bn here, and in this case, Bn different from 0. So we need to put also Bn. Okay, so that reason we got this one. And on another thing, another form, this is an observable canonical form, but actually this is a transposed of the canonical form. Okay, controllable canonical form is then we can observe that the observable canonical form equal to this, the transposed of this, transpose this, transpose this. And this doesn't change. Okay, so we got some example about it. And next, we got another thing in diagonal canonical form. This is a very good representation because when we try to calculate the solution of the state space equation, so if we got the diagonal canonical form, then it's easy to solve. Okay, but this form is only capable for the k that we got. We assume that the denominator here have the distinct roots. All P1, P2, and up to Pn are different, meaning that P1 different from P2, different from Pn. Then we can put in this form by rewrite the polynomial in this form. Okay, C1, C2, Cn, and I also show you that we can, if we got this, then they can represent the system in this form. And we have diagonal system matrix A like this. Okay. So if you got this one, then all of this is 1, 1, 1. Okay. And in C matrix, we'll have the constant of this fraction. Okay. And we have some example about it, and I show you how to find C1, C2, and C3. And the formula for this is this. And we'll all practice on this. And we have the first example, and also some practical problem, and we find the solution easily. And I also show you that we got some cases that even the numerator, the order of the numerator bigger than the orders of the denominators, we still find the polynomial representation of S like this. But this is not exist in a technical problem, because for the technical problem, it only require that M smaller than equal N. The orders of the numerators is less than or equal the order of denominators. Okay, so we just represent it in this form, but we will not use this. And the reason why we try to get the diagonal canonical form is this. When we find the solution of the homogeneous solution of the state space equation, we all know that the homogeneous solution is H of T. So sorry, X8 of T. This homogeneous. Homogeneous means we have no input. Okay. Then we have to find transition matrix T and multiply by the initial condition or initial of X naught, or this is a E A of T X naught. Okay, but the calculation of E power of AT is not easy. Okay, so normally we present AT equal something like I plus AT and divided by fraction in naught plus something like this. So this is to calculate this is not so easy. But if we can represent A in this form, then we can find this so easy like this. Okay, so that's the reason why we try to get the diagonal canonical form. Okay, but unfortunately, this is only happen if the denominator have the distinct root or distinct solution. There's a requirement for that. Okay, so we require that P1, P2 up to Pn is the difference. They are all different. So in case that we got some identical solution, then the diagonal canonical form cannot achievable. Okay, so we have to find another form, canonical form, and this Jordan. Okay, so in Jordan canonical form, I have changed something a little bit to explain things to use better. In the last lesson, I have an example of, okay, we got here is, for example, P1, triple, and then we got here S plus because we have P1, P2, P3, so we have P4. This is in the denominator, we've got S plus P5, and so on, up to we got here is S plus Pn. Okay, so for generalization of this problem, I assume that the power here, we got the identical solution, and the number of the identical solution is n. For example, like this. So we got SP1 n, and then we got S plus Pn plus 1, and then we get this is a Pn plus 2 up to S plus Pn. So this is the generalized version of this if we got only one. This is only one multiple solution, and we got the identical one, and in this case we have only one, but we have the S plus 1 n identical matrix as a solution or root. Okay, and in this case we can represent the system, the transfer function in this form. Okay, I will write this a little bit. If you look some books, they denote it by C11, C12, and C1n. But I assume that we got 3, but we got more, and we got more. Then if we denote it by C1n, and here we got C2, C3, up to C, for example, C10, and we repeat C1, C11, C12 again. So in this case, you see that we got 2 C11 and 2 C12 and more. So I think this is not good notation. So I change it into C0, C01 here, C02, and C0n. Okay. And then we got Cn plus 1, Cn plus 2, and Cn. Okay. So if we denote, okay, I think it's better. Then we got the Jordan canonical form written in this form. Okay, so we got a repeat block. So this we got I denote this, meaning that we divide it into some block. Okay, the first block we got 4. Okay, so this is we call it also a Jordan block. We have a Jordan block. Okay, and it contains all the repeated solution or root. Okay, and here we got more root. Okay, but distinct root up to Pn plus 1, Pn plus 2, up to Pn. Okay, so they have the from here we got this is a distinct root, and this is a multiple root. Okay, so we got this, and in this form, and we also denote it by x1 dot, x2 dot, up to xn dot. Okay, and then we got xn plus 1, xn plus 2, and xn. Okay, and here we got all the distinct, all the identical root before n got 0 here. So we got 0, 0, 0, and for the last one, we put 1 here. And then for all of this is correspond to the distinct root. Okay, and this is the problem with notation. And we got here with C01, 02, and up to 0n. Okay, so we have n plus 1, n plus 2 up to Cn. Okay. But in the last lecture, I already told you that in some cases, or I'm not checked yet, but in some case, because Jordan form here, also when written Jordan block, in some cases it look like this. It's still like this, so we have 1, 1, 1 here. It depends on the presentation, but we have to check this again because in the next section we will take the inverse direction, because here we got transfer function and we change it to the canonical form. Okay, and now we will check again by using canonical form, some kind of canonical form. We will translate it or transform it into TF to check whether the correct or not. Okay, from transfer function we put the canonical form, and now we got canonical form, and we take the transform, inverse transform to the transfer function to check. Of course, this should be this. Okay, they have to equivalent. So this is a way we will check whether or not we represent the system correctly. And I also give you an example in the class. I didn't prepare this first, and I make something wrong on this. But finally, when we take again and we find this solution, I already put it in the yellow group, and you already know that we can find this is C1, C2, C3, and we find the solution that C1 is 2, C2 is minus 1, and 3 is 1. Okay, so we can represent it in this form. We have the 1, 1, 0 here, or 0, 0 here, and 1 here. Okay, so but we got this Jordan block here because this is repeat 2 times. Okay, so we got this one, but I think I don't check another form yet because I put 0 here, 0 here, and I will check with 1 here. Because why? Because this here is we have A equal. Here we got diagonal form with minus 1, 0, 0, 0 here, and 0, 0 here, minus 2 here. And if we have to check next, we already know that the transfer function ds equals c as I minus a minus 1b plus d. We got this before, so if we take the inverse of this, it's easy because we got c. Okay, so has this is a s. So this is a identity matrix. So we got 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay. Minus a, in this case, is a is minus 1, 0, 0, 0, minus 1, 0, 0, 0, minus 2, and inverse. B, in this case, is 1, 1, 1, and this. Okay, so if we write this form, it's easy for calculating because we got C in this case is 2 minus 1, 1. And here we got, okay, so S multiplied by this, we got S 0, 0, 0, S 0, 0, 0, S minus A minus 1, 0, 0, 0 minus 1, 0, 0, 0 minus 2. Okay, inverse. And we had 1, 1, 1 like this. So we got here is 2 minus 1, 1. And inside this, we got, you see, we will see that, okay, S minus 1, S plus 1. And other place is 0, 0. And also here we get S minus 1, S plus 1, and 0, 0, 0, S minus 2, s plus 2 minus 1. 1, 1, 1. Okay, so we got the diagonal form here. So we'll take the inverse. The inverse of the diagonal matrix is the inverse of its elements in the main diagonal main the main this. Okay, in this form we easily find that is minus 1, 1, and here we have 1 s plus 1, 0, 0, 0, 1 s plus 1, 0, 0, 0, 1 s plus 2. Okay, and here 1, 1, 1. Okay, so we multiply this when we got 2. And here we got this, multiply this is 0. So we got here a 2s plus 1. Okay, and here we got 1 minus 1 here. Minus 1 s plus 1. And here we got 1 s plus 2. This multiply this is 0, this 0. Okay, and here we got 2, 0, minus 1 here, minus 1, 0. And here for this we got 2, 1, 0, and 1 of this. Okay, and here we got 1, 1, 1. Okay, finally we got this multiplied by this multiplied by plus this, and this multiplied by this. So we got 2 s plus 1 minus 1 s plus 1 plus 1 s plus 2. And we check this and it correctly because we represent this in this form. Okay, and it's correct. So this form, when check with this, so we've got this form, but only in case that we represent is in the diagonal form like this. Okay. So, so this is something about the canonical form. Okay, and actually, if you, I don't know whether or not you learned this in the calculus 1 or 2, but sometimes for this form, not take care of this, of C, we see x plus du, but we do care about A, okay, the system matrix A. And if we got the matrix A is not in a Jordan form, or it's not in, for example, canonical, a controllable canonical form, we represent A in difference from the canonical form, not in tunable canonical form, observable canonical form, or diagonal canonical form, or other form like Jordan or other form. Then we can transform this in the canonical form. Okay, and when we do this in this section, we see that we have no formula to transform this into the canonical form. It depends it depends on the particular model, okay, in particular system, and we do not have the systematic way to calculate the canonical form from the representation of A. Okay, but when we calculate this from something like this, and something like I represent you this methods. Okay, this is one way but this is not good way. Okay, I don't think this is good way. We can calculate, or we can find the Jordan canonical form. We can find diagonal canonical form, but it's not the way we will use in reality. Okay, because we have another way, and it's a better way to calculate or to compute, or we can find the canonical form is based on the eigenvalues or eigenvectors. Okay, and they have some features that we can use. That is the reason why we actually I show you the methods how to calculate this form by hand. We will not do this, okay, in practical issues. Okay, so that's the reason why I do not have more example for use to practice on. Just familiar with this and familiar with the way we can find the canonical form. But in a better way, we do not use this. So we have to look at the eigenvalues and eigenvector, and I will show you how it related to the canonical form later. Okay. Okay, so I will check Zoom again, and I will put everything. You are in the waiting room, and if someone come later, you have to ask me to go to join the class. Okay. Okay, I told you before you need to reviews about eigenvalue and eigenvectors because you have been given this nature in calculus 1 or calculus 2, I think. So I will introduce this. This is an application of the eigenvalues and the eigenvectors in the control system theory. Okay, first we will have the definition of eigenvalues. The eigenvalues of square matrix A. So this means that the matrix A should be square, and it's always in the control system. We have this A, and it defined as the root. The name of the root is lambda I of the following characteristic polynomial equation. So we got the determinant of lambda I minus A equals 0. Okay, and here we got I is identity matrix. Okay, and have the same sign as A. So we normally, and you can represent A as in, for example, in a real space with all numbers are real, then the identity matrix should be IN. Okay, the same size, or IN or IN and by N. It doesn't matter because we already know that identity matrix. So this is a definition of the eigenvalues. For the eigenvectors of square matrix A associated with the eigenvalue lambda I of the A defined the vector that satisfies this equation. Okay, A Vi equal lambda I Vi. Okay, so first we need to find the eigenvalues, and then we associate this eigenvalue to the eigenvectors. Okay. For example, if the system like this, so this is A matrix, you have to find eigenvalues of this. Okay. So to find this, we'll apply this, the characteristic equation, determinant of characteristic equation. We take first lambda I, and lambda I here minus A is a system matrix, and find the polynomial of lambda here, and then find the solution of this. They will find the eigenvalues. Okay, so this is another way to denote the determinant. Okay, you see, we got the determinant of lambda I minus A. You see, okay. So we solve this equation, and then we got this is a lambda I. Okay, so we got here. Okay, lambda I minus A. Lambda is lambda because this is a n by n is 3 by 3. So we got 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, minus A is this 0, 1, 0, 0, 0, 1, minus 10, minus 9, and minus 4. Okay, so in other words, we got lambda 0, 0, 0, lambda 0, 0, 0, lambda minus this 0, 1, 0, 0, 0, 1, minus 10, minus 9, and minus 4. And what we got is this. We got the two matrices. We subtract this matrix from this. So actually, we subtract all of their elements. Okay, so we got lambda minus 0. We still got lambda 0 minus 1. We got minus 1, and so on. Okay, and finally, we got this. Okay. So we have to determine a determinant of this, and we find this. Okay. And this is an example of this. So we have to find the determinant of the 3 by 3 matrix. So we got this one, and then we can rewrite this one in this form. Okay. Or in other words, this is how we have the third order polynomial of lambdas. Okay. So this is the highest order of lambda, and you find this solution. So actually, this is a first root, and this is a second root. This is a third root, and this is a, we got the C, lambda 1 is minus 2. The second is this, and the last one is this. Okay. Any question, please?
No, sir.
No, sir.
Okay. Okay. So another example. Okay, in this example, we have to specify the eigenvalues and eigenvectors associated with this matrix. Okay, so we know how to find eigenvalues. And okay, so we repeat this. Again, we calculate the determinant of lambda I minus A, like this. And we find this, and we find this. And in this case, easy because this will have only second orders. Okay. So in this case, we'll find that the first eigenvalues, number 1 is minus 1, and the second eigenvalues, number 2 is minus 4. Okay. So we will find the eigenvectors. For the eigenvectors, we all will have this. Okay, we got A VI for example, for the first, we have A V1, A lambda 1 V1. Okay. Okay. So again, we got the first vectors will be A V1 equal lambda 1 V1. Okay. Or we can move. Okay. This into the right hand side, then we want to rewrite this is lambda 1 I minus A. Okay, V1 equals 0 because we move this into the right hand side and we have the same V1 and put V1 outside and then we got this. Okay. Okay, so for the K, lambda 1 is minus 1. Then we got lambda 1 I is lambda 1, 1, 0, 0, 1. Okay, so we got lambda 1, 0, 0, lambda 1, but lambda 1 is minus 1. So we got minus 1, and this is A, and this. And it should be 0. Okay. But in this case, we will find that, and when we solve it, we will see that, okay, we assume that V1 in this case, we assume that V1 equal V11, V12, because we got 2 by 2 of A, we have A 2 by 2. So this is V1. So we have V11, V12. When we solve it, we will see that the first equation will be V11 equal V12. And the second also give V11 equal V12. Okay, we show this. You can find this. Okay, because why? Because this is, you see that this is a minus 1, minus 2. Then we got minus 1 and plus 2, we got 1. Okay, so 1, V11. Okay, and here we have minus 1 plus minus V12 equals 0. So we got V11 equal V12. And the second one, we have the minus 2, 3. So we got V11 equal V12. Same. Okay. So we can, in this case, you can find that we can put any value of V11 and takes V12 the same. Okay. So meaning that V1 can be written in this form, alpha 1, alpha 2. Okay. And the requirement is that alpha 1 different from 0, any values. Okay. But the requirement is that the first element equal to the second element. Okay. For the lambda, okay, so I think that should be better if we put this is the number 2.
So I can hear you.